Here it says pause, but I don't know what that means. Oh, no, that's share. That's fine.
Okay, so it's recording.
I'm not sure. This is something else. This is another timer.
Because
This is the recording thing. Oh,
okay, so
yeah.
it's okay.
Seems like it's recording.
I'm happy to I'm happy to introduce Professor Paul Wedrich from the University of Hamburg. And as you can see, there is a research center there, higher structures, moduli spaces, and integrability. And Paul Wedrich is one of, he's on the management committee. He's also one of principal investigators in the cluster center, in the cluster, how to say it, the research cluster of excellence, the research cluster of excellence, quantum universe. Most of his work concerns categorification in quantum topology and connects low-dimensional topology and representation theory. In particular, his recent work focuses on the connections between homology and topological quantum field theory. This includes a new class of 4 manifold invariants that he developed in a joint work with Morrison and Walker. These invariants are seeing a lot of interest currently because they provide the first analysis-free proof of existence of exotic, compact, orientable 4 manifolds. Professor Wedrich obtained his PhD in 2015 from the University of Cambridge. And then he had some research positions, in particular at the Max Planck Institute in Bonn. Currently, he supervises 5 postdocs and 4 PhD students, which is genuinely impressive. Okay, please, Paul, the Zoom and the floor is yours.
Yeah, thank you for the kind introduction. So I should say in Hamburg, there are lots of people with related interests, and all this supervision is really good teamwork. So I don't. This is not all me. Okay, so thank you very much for the invitation and the opportunity to speak here. The title is Knots and Categories. That's a bit vague, but we'll get right into it. And my idea for this talk was to give you some kind of a broad overview over where the subject is coming from, and then maybe at the end outline a few directions in which this is going. So let's see, I have to click something. Maybe I have to do the thing. Yay, here we go. Okay, fine. So the first topic of the talk are knots, links, and tangles. And I'm based in Hamburg, and this is a very maritime city. And it has this historic harbor, and it has a long history of seafaring. And so it's not surprising that one sees the nautical uses of knots in everyday life. For example, on this museum ship Peking, this 4-masted bark that has arrived a few years ago in the harbor. So on the right-hand side, you see some of the running rigging of Peking, and it is neatly coiled and secured. When in use, however, pieces of rope naturally get tangled and knotted up. Everybody knows this, right? So kind of from old-fashioned headphones and so on. For example, when you're sailing in a windy night through the English Channel on a more modern sailing boat, you might see a tangled mess like this. And then it's really time to start untangling everything and cleaning up. And this tendency of pieces of knots, pieces of rope to knot up is something that happens on all length scales. So for example, in the 1980s, biologists found out that bacterial DNA, which is special because it forms closed loops, can get knotted up. And in fact, there are certain enzymes, they're called topoisomerases, which are constantly adjusting the knotting and linking and twisting of bacterial DNA and also of our own DNA as we're sitting here. If these enzymes get blocked in their action, the affected cells cannot replicate for topological reasons, simply because their DNA cannot go into different nuclei. And this is used in an important class of antibiotics and in certain anti-cancer drugs. Knots can also arise in the folding processes of proteins. Another totally different way knots show up is as data structures. So a historic example of this are the so-called quipus. These quipus are kind of assemblies of knotted pieces of string that were used by the Inca for data collection and storage. And they were used in an environment where long-distance transport happened on foot over mountain passes and trails. And the fact that the knots in these strings persist, they just stay there where they are, even when you shake the entire bundle, which can happen if you go over a mountain. This feature that the knots stay where they are makes the information storage durable. Yeah, and interestingly, in a similar way, knotting and braiding also plays a role in modern information processing for a very similar reason. In topological quantum computing, logical gates are modeled using the braiding of certain quasi-particles in 2+1 dimensional space-time, and the topological nature of this braiding makes the computations fault tolerant. So these are kind of places where knots and links and tangled objects appear in other places, in other sciences. But today we will see knots and links as topological objects in math. So in topology, a knot is defined as an equivalence class of smooth embeddings of the circle, denoted S1, into three-dimensional space. And that could be either R3, or it could be its one-point compactification, the three-sphere S3. The equivalence relation that's imposed is ambient isotopy. That is a continuous deformation of the ambient space, so the three-dimensional space, taking one embedding to the other. Usually, we think about knots and links by means of their two-dimensional projections onto a drawing surface, like this one here, or onto our retinas. A few examples of small knots are pictured here. So the one on the left, maybe I have a pointer here. Yeah, this one is represented by the standard embedding of the unit circle in the complex plane, and that's sitting in R3. So this is called the unknot. It's the simplest knot. It's also called a trivial knot. Next to it, rotating, is the trefoil knot. It's related to the knot that we tie on our shoelaces. And if you're maybe a climber or a sailor, you might also know this other, the next knot. This is called the figure 8 knot. And then there are a few more knots with more and more crossings, and this never stops. And slightly more generally, one can also consider embeddings of some finite number of circles, not just one, and then one arrives at the concept of links. So here in the bottom, we see two links. On the left is the Hopf link, consists of two unknots which are linked up. And on the right, we see the famous Borromean rings. So there are three unknot components, and they're linked in a very interesting way. If you remove one of them, then the other ones can be separated from each other. So when I saw these kind of knots and these definitions for the first time, I was really puzzled about how mathematics could say anything useful about these things. So how could this work? So how do we study knots in math? For this, to motivate this, I want to make a bit of a digression here. Let's think about how one can study groups. Well, there are many ways of studying groups, but one way is in combinatorial group theory, we study groups by means of their presentations. So we can think of groups as describing symmetries of some object. For example, let's consider this equilateral triangle. So if you play with this equilateral triangle, maybe you have a little model in mind, you can convince yourself that the symmetry group has 6 elements. They're made up out of 3 reflections and 3 rotations, where one rotation is a trivial rotation. So this will form the dihedral group D6, or equivalently the symmetric group S3. So here we see, let's see, so here we see 2 reflections in these lines. And it turns out that all the symmetries can be written as composites of these 2 reflections. So for example, we can take the empty composition. So this is the identity. We have the reflections S and T, and then we have the composites ST, TS, and STS. So in this, if this is the case, if all symmetries can be written as compositions of some fixed set of reflections, we say that these generate our group. But knowing these generators is not enough. We also want to know, it's not enough to determine the group completely. We also need to know what sort of relations are satisfied by these generators. So in this particular example, every reflection is its own inverse. So that means it squares to the identity. So S squared equals identity and T squared equals identity. And we also have the relation STS equals TST, which are 2 expressions for the reflection in the red line, which we haven't considered before. Yeah? This is the notion of a presentation of a group. It encodes the data of a group in terms of generators and relations. And this is it's a very useful concept. For example, if we want to study group homomorphisms out of our symmetry group into some other group G, the only thing we need to do to write down such a thing is to say where the group homomorphism takes the generators, and then we need to verify that the relations are satisfied among the values of our function. And now the question is, can we find a similar way of dealing with knots? Yeah? So here we found presentations for groups. Is there a presentation for knots? And the answer is yes. So knots and links can be presented by diagrams, the pictures that we've already seen. And a link diagram arises by projecting the image of the embedding onto the 2-dimensional drawing surface. And then additionally, we need to remember at every crossing which strand goes over and which strand goes under. Okay. And then, of course, a link or knot can have very, very different looking diagrams. If you think about a tangled mess of strands here, if you look at it from different directions, it will look very different. And we are all familiar with cases where some, I don't know, very easy knot, for example, an unknot, looks completely tangled up. So in this sense, link diagrams are a bit like words in the generators in a group presentation. It can be quite hard to tell whether a word in group generators represents a trivial element of the group. So we want to know when 2 of these expressions represent the same object. So we want to know relations between these knot and link diagrams. And the relations can be described by a famous theorem of Kurt Reidemeister from around 100 years ago. Actually, so around the time when he graduated as a graduate student in Hamburg. Now, the theorem says that 2 diagrams represent the same link if and only if they are related by a finite sequence of moves that we now call Reidemeister moves. So they're pictured here. There are 3 types of moves. In a picture, you can replace a single strand by a little curl or the other way around. If you see 2 parallel strands, you can pass one over the other. And if you have 3 crossings in such a configuration, so 3 strands crossing each other, then you can pass 1 strand underneath another crossing. So in this theorem, one direction is really easy, and the other one is the hard, interesting one. The easy direction is this. So if you have 2 diagrams which are related by one of these moves or by a finite sequence of such moves, well, then clearly they represent the same link. You can find an ambient isotopy which will do exactly this. The interesting direction is the opposite one. Whenever 2 diagrams represent the same link, you are guaranteed that there exists a finite sequence of moves that takes one to the other. And this gives a presentation of knots. In another paper around the same time, Reidemeister mentions a well-known problem in topology, namely to decide whether 2 knots or whether 2 embedded circles or 2 pictures of such, so 2 diagrams, represent the same knot or if they do not. For example, here are two very similar looking diagrams. They all look a bit like a trefoil. And we can ask, are they the same or not? Okay, can I find a sequence of moves, or can I find an ambient isotopy that converts one to the other? Do you see the difference? Okay, I see nodding. Excellent. So Reidemeister's theorem gives us a possible strategy to prove that two such embeddings represent different knots. Say we're convinced that they're not, they shouldn't be the same. How are we going to prove this? So what we can do is we can consider functions from the set of all possible link diagrams to some other set S. We say that such a function is a link invariant if it is constant under changing diagrams by Reidemeister moves and some planar isotopies. If this is the case, the function factors through a function from the quotient set, namely the set of links, to the set S. So defining such a function is similar to defining a group homomorphism from a group with a presentation. We say what it does on generators, and then we check that it is constant on the relations. Check that the relations hold in the image. And now, what's the strategy to prove that these two diagrams represent a different knot? Well, we have to look for a function that happens to compute different values on these two inputs. And if they compute different values, then we have a certificate that the diagrams represent different knots, because if they were the same, there would be a sequence of moves under which the function would remain constant. Contradiction. So this is not an if and only if statement typically. So if the function happens to give the same values, then we can't deduce anything typically. There's a question.
The S is something definite, or is it like any set?
It's open to your creativity.
Okay.
Yeah, it will be different in different cases. And sometimes it will not be a set, and that's the point of the second word in the title of this talk.
Oh,
Yes.
okay. Thank
you. Yes. Okay, great. So this is all fine, right? This would be a nice strategy. The question is, where do we get such functions f? Okay, ideally interesting functions f. I don't want to have a constant function. That would be a bit useless. We can try to use algebra to find such functions f. But for that, we should have an idea what sort of algebraic structures are related to knots and links. I think there's another question.
Yeah, sorry. So you have said that S need not to be a set, yes? So you think about something like a big category? Or?
Yes,
Oh,
yes.
okay,
well, I'll
okay.
get there.
Okay.
You're ahead. Okay, good. Okay, so I want to go slow. So first we do a bit of algebra, okay? So we need to find algebraic structures related to knots and links. So here's the first try. So a very famous answer how knot theory is connected to algebra comes in the form of Artin's braid groups. So let's fix a natural number n and consider configurations of n strings running from bottom to top in a box, say, and they can cross over each other and under each other, but they end up somehow in the same places at regularly spaced intervals. These are called braids, and they can be stacked on top of each other to make a new braid. And this gives you an associative multiplication. And the trivial braid, which is the braid that doesn't have any crossings, it consists of strings that run upwards, straight, is somehow neutral, the neutral element for this multiplication. Furthermore, if you consider these braids up to isotopy, every braid has a multiplicative inverse. Namely, you just undo the crossings in the opposite order. And that generates the so-called nth braid group. In this paper where this gets introduced, Artin writes down a presentation for the nth braid group. The generators are the individual crossings between the strands. So you can cross the ith strand over the ith plus first strand, and the inverse would cross under. And there are a bunch of relations that look very similar to the relations in the symmetric group that we've seen. Namely, you have some sort of an STS equals TST relation, which is secretly the same thing as the third Reidemeister move. You have the fact that if crossings happen on strings that are far apart, they will commute, so they can change the height. And then we're conspicuously missing one relation that we had in the symmetric group, namely the generator squared to the identity. That's not the case here. So if you pass a strand over and then you pass them again over again, now they're twisted up and they're not undone. So this is how symmetric groups and braid groups differ. So these braids now really form a group, and they can be studied using group theory, actual algebra, right? But they're also related to knots and links. And this connection has two components. The first one is a classical theorem of Alexander that shows that any link can be represented as the planar closure of a braid. So consider a braid drawn like this. I draw it in this little square, and then I close it off in a planar fashion by adding some strings, connecting the top endpoints to the bottom endpoints through some untangled strings on the outside. Okay, so this way we can obtain every link as the closure of some braid. And of course, this is not unique. And there's some ambiguity, which is classified by or characterized by another theorem, this time of Markov. And so that theorem says that braids with the same closure are related by so-called Markov moves. So if you have, so this is a bit like the Reidemeister theorem, but this time for braid closures. Braids have the same closure if and only if they're related by a finite sequence of such moves. What are they? You can conjugate braids. Yeah? And you can also, there's also a type of move which allows you to change the number of braid strands. And if you think about what this move does, if you look at it, think about what this does. After you close up, you see that they're related by Reidemeister 1 moves. Now, as a corollary of these two theorems, we can obtain the following. If we get a braid invariant, so a function out of all the braid groups to some set, which happens to be constant under changing the braid by one of these moves, or by all of these moves, I should say, then this gives us a link invariant. Okay. Make sense? I see nodding. Good. Okay. So now we're getting closer to interesting link invariants, but we're not quite there yet. So next, I want to show you one of these invariants. So the Jones polynomial was discovered around 1984 by Vaughan Jones, and he used braid groups to construct this new knot invariant. And this was a monumental discovery that started several new research directions and which, for amongst other things, earned Jones a Fields Medal in 1990. So this, curiously, this Jones polynomial has a very elementary description that I want to show you. So there's an algorithm that does this. And it goes like this. So as input, this algorithm takes a link diagram, and we have to fix some invertible scalar A in a ring. So this could be like a non-zero complex number if you want. And then we modify the link diagram according to two rules. We're allowed to replace crossings, and we're allowed to replace circles in the picture. And then we apply these rules until we get a number. And I want to show you on the board how this works in an easy case. So let's see. So I think this board is fine to use, right? On this side.
No. Please write on the tablet, because on Zoom we don't see the board so well.
Oh my God. Okay, let's try. Okay. But this will, tablet, let's see. I can draw on the tablet. Okay, let's see. So I want to consider, let's see. No, this is terrible. Okay, that's a hop flank, right? Now, I'm focusing on the top crossing first, okay? And I have to replace this, according to the rule here on the right, by linear combination of diagrams. So I'm gonna write down an equation that takes place in formal linear combinations of diagrams. So I'm gonna do A times, and I have to replace the top crossing by, well, this picture. So what I'm gonna get is, let's see if I can do this. That picture. And then I get A inverse times if I replace it in another way. So it's gonna look like this if I do it correctly. Yeah, make sense? Okay. And then these diagrams still have one crossing, so I can play the same game again. if I do this for the first one, so I'm going to take A times some other stuff. So I'm going to replace the remaining crossing that I see here by the picture which is where the strands run vertical. And then I also have to replace this by A inverse times the picture where the strands run horizontal. So then I'm done with the first picture. And then I still have the A inverse term. And what am I going to get there? So we do A times the vertical resolution. And then we do A inverse times the horizontal resolution, which now looks like this. Okay? Happy? So I've somehow replaced the crossings in the diagram in a multilinear fashion by this expression. And now what I see is some formal linear combination of diagrams which only consist of circles. And now I'm going to introduce delta here, because that's easier to write than this expression. And well, if we expand everything, I'm going to see A squared times delta squared. So if you have two circles here, this counts as delta times delta, because a single circle is delta. Then we get A times A inverse delta, so just delta. Another A inverse A delta, so another delta. And then we get plus A to the minus 1 times delta squared. And if you expand this out and plug in what delta is, then, and I do this. If you expand this out, what you should get is A to the 6 plus A squared plus A to the minus 2.
Should it be A to the minus 2?
A to the minus 6. A to the minus 2. Thank you. Yeah, exactly. So if A was a complex number, now you've computed a complex number associated to that Hopflank. Okay, so that's just how this works. So we've done this as an example, and now the amazing thing is, well, this took as input not just this fixed value of A, but also a link diagram. But it turns out that what you get out is constant under the second and the third Reidemeister move. So it's almost a link invariant. You can also fix, so under the first Reidemeister move, it changes slightly, but that can be modified away. And in this way, you can get a link invariant. It's called the Kaufman bracket, and it's very closely related to the Jones polynomial. Okay, now a few comments are in order. First, this Jones polynomial is actually a Laurent polynomial in this variable A, and it has integer coefficients. So you can take, you don't have to pick a complex number. For A, you can let this Jones polynomial take values in a Laurent polynomial ring in one variable A over the integers. So when this was discovered, it was immediately somehow a question what this thing means intrinsically. This was a question that was posed by Sir Michael Atiyah, and Edward Witten famously gave an answer in terms of Chern-Simons theory in physics. And for this, he also received, amongst other things, he also received the 1990s Fields Medal. From this Chern-Simons perspective in physics, it's a bit unclear why the Jones polynomial has integer coefficients. In the algorithm that I showed you, this is completely clear. We only used integers. But if you take the physics route, it's not clear at all why this has integer coefficients. This was the starting point for a research field called quantum topology. Going back to this topological quantum computing idea, is one interesting fact, namely that approximating the Jones polynomial at a complex root of unity is one of the problems that a quantum computer could solve efficiently. It is, one says that it's BQP complete. So yeah, it's something that it's kind of a universal decision problem that a quantum computer can solve in polynomial time up to bounded error.
And what do these letters BQP stand for?
I don't remember.
Okay, but Q for quantum for sure.
Yeah.
B stands for bounded, and
bounded quantum polynomial. Okay.
Yeah,
thanks.
That kind of makes sense. Yes.
Okay, thanks.
Yep. Okay. So even though this invariant has this super easy description that I showed you on the previous slide, there's some unsolved questions about this invariant. So, for example, from the algorithm on the previous page, we know that the Jones polynomial of the unknot, yeah, the trivial circle, has invariant delta, which was this minus a squared minus a to the minus 2. Now, it's unknown whether any other knot has the same invariant. So this is called the unknot detection problem. If you give me a knot, I compute the Jones polynomial, and it happens to have the same value as the Jones polynomial of the unknot. Can I now conclude that the knot is the unknot? Who knows? So I want to take a step back and look at an alternative way of turning knots into something algebraic. And this is the story of addition of knots. So suppose we have two knots that we want to add. Then we can pick a point on each of them, cut the knot open close to that point, and then reseal them in a different way to make a new single knot. So for example, here I show the sum of a positive 5,2 torus knot and the negative trefoil. And this is known as the surgeon's knot. It's actually used in surgery. If you have gut sutures, it gets knotted up like this. So it's a fun exercise to check that this addition of knots gives a well-defined binary operation for oriented knots that is commutative and associative. Also, the unknot is a neutral element. So this gives the set of knots or oriented knots a commutative monoid structure. For a given knot, that now allows us to ask whether it can be written as a sum of two non-trivial knots. If not, then we call it prime. And in tables for knots that have been compiled for more than 100 years, and which you can find online, and they're very picturesque, we only list prime knots because the other ones can be built from them by addition. So here's a little exercise for you. I've written two sums of knots here, and can you spot the difference? I see some nodding, yes, okay. So what's here on the left, we see the so-called reef knot. It's also called the square knot. And on the right, we have the so-called granny knot. The reef knot is used in sailing to secure reefed sails using reefing lines or sail ties. If you do a sailing course, people might tell you that it's also a good way of connecting two ropes of the same diameter. It's actually not good at that, but okay. In any case, it's significantly better than the granny knot. And there are two main advantages to the knot on the left-hand side. It's more secure when you pull load on it. And it's easier to unknot again after it's been loaded. And why is that? Well, the reason is that this reef knot somehow has two bites here that you can use to break it open, even if it's been under a lot of tension. So you can pull it loose. And these bites you don't have in the granny knot. The granny knot will somehow knot up in a completely different way. And this distinction, surprisingly, is mathematically significant. So one says that the reef knot is slice, but the granny knot is not. To explain what this means, we have to think four-dimensionally, at least for a little bit. So a knot in the three-sphere is called slice if it is the boundary of a disk, which is smoothly embedded in the four-dimensional ball, whose boundary is a three-dimensional sphere in which our knot lives. So 4 dimensions are completely essential here, because in 3 dimensions, the unknot is the only knot that is the boundary of a disk. In 4D, interesting knots, like the one on the left, can be the boundary of a disk. So to show you how this can be done, let me try to draw the disk for you for the knot on the left. But first, we have to prepare the knot a little bit. So the first thing I do is I pull the top string to the bottom. And then I pull a bit more of the rope to the bottom. And now we see 2 parallel strings here at the bottom. And now we can start drawing the disk. So I will indicate the disk by a little bit of shading. I hope you can see it. Yeah. And so we start to fill the region between these parallel strands. Okay. So I'm gonna keep drawing. And you see now these pieces of disk are on a collision course. right? So I have to start using different shadings to tell you somehow which part of surface is coming from which side, and soon they will be colliding. So we're going to stop on the right-hand side, but continue with the part of the disk that comes from the left and try to fill up as much as possible. So let's let this keep going. And now it wants to keep going, and so on and so on. Well, now if you reach the end, so it's now completely filled up. So the bit that came from the left is now completely filled up. I'm done with this part of the surface, and now I continue with the stuff that I've parked that came from the right. So let's let this go on, and so, oops, now I've created a collision. Right, so this piece of surface had to pass through the surface that I've already drawn, and the intersection I've drawn in red. Okay, but then we want to continue, and oh, we've created another collision, another interval. So at this point, we do have a disk, and it sits inside three-dimensional space, but unfortunately it has some self-intersections at the red intervals. This is called a ribbon disk. It's not embedded. It has double points. But here we can use the fourth dimension to come to the rescue. So we have an additional coordinate that we haven't used yet. Okay, so the three sphere sits here at the boundary of this four-dimensional ball. There's some radial coordinate, and so far I've just worked in constant radial coordinate. So what we can do is we can slightly push part of the surface that we've drawn here in the interior of the four ball to resolve the intersection. The question is how I'm going to draw this. Well, I can use color as somehow my encoding for the radial coordinate. So I changed the color. I changed the coloring of the shading from gray to blue to indicate that the radial coordinate is now less than 1. So I push it into the interior of the four ball, and now it's still a disk. And now it sits in the four ball, and its boundary is that knot. Okay, so we see that the reef knot is slice. Okay, so using smooth surfaces in 4 dimensions, we can make our knot sum operation, this addition, a little bit more interesting. And this is the story of concordance. So 2 knots are called concordant if there exists a smoothly embedded annulus in the 3-sphere times interval, whose boundary on one end is the first knot, and whose boundary on the other end of the interval is the other knot. And this is an equivalence relation, as you can convince yourself. So a knot is slice if and only if it's concordant to the unknot, because then we know we have an annulus to the unknot, and then we can cap off with a disk. So if you glue an annulus to a disk, you get another disk. And any knot now has an additive inverse if we mod out by this equivalence relation of concordance. The inverse is just somehow a reflection of the knot. And when we quotient out by this equivalence relation, we obtain the so-called concordance group. And this is a very interesting group. Let's go. Yeah, please go.
So you presented very nice pictures and diagrams of those nodes, but do we have, I suppose surely we have a more systematic approach to such calculations, like for example calculation of the fundamental group of what is left of our R3 in this case when we cut out our knot and so on, because if we go to more complex example, we may easily lose our intuition when we use these diagrams that were in this original work you presented. This work that you had on slides in German, yes?
Yes. So that's a good exercise. So we've seen group presentations. You seem to know fundamental groups. So now it's an exercise to compute a presentation for the fundamental group of the knot complement from a diagram. You can do this. You can also look it up. Yes, there are ways of doing this, but your question raises an interesting point, and that is what is really the appropriate data structure for knots and links? And diagrams turn out to be pretty close to it. But maybe I'll go into this after the talk. Yeah.
Okay, thank you.
Yeah. All right, concordance group. So I want to go back to this comparison of the reef knot and the granny knot. So we've seen that the reef knot is sliced, and I've claimed that the granny knot is not sliced. So how on earth are we gonna convince ourselves that this is true? How do you prove such a statement? What's a bad strategy? A bad strategy would be to try to look at all embedded disks in the four-ball and see that none of them has this as a boundary. That's not gonna work, right? It's a terrible strategy. Proving non-sliceness of knots can be extremely hard. There are knots for which proving non-sliceness would give a counterexample to the smooth four-dimensional Poincare conjecture, which is probably the most famous open problem in low-dimensional topology. For the granny knot, though, non-sliceness is known, and it's actually not that hard. So I want to show you one solution here, which is definitely overkill, but which works. So why not do it? So first of all, we have to convert our knot into some kind of data structure that the computer can handle. Let's write it as a braid closure. We've
Sorry,
seen
just
that this is
briefly,
possible.
could you repeat those connections with Poincare conjecture? Smooth?
Later, okay?
Okay.
Yeah, good. So first we write the granny knot as a braid closure. And then I feed the braid word into a computer program that the colleague of mine, Lukas Levark, has written. It's called COCA. Lukas is based in Zurich. So this program, what will it do? It will compute a spectral sequence. More precisely, it will compute the E-infinity page of a certain spectral sequence. And it will spit out what the Poincare, graded Poincare series of the infinity page of that spectral sequence is. So I'm interested in the Q grading of a one-dimensional vector space that appears at this E-infinity page. So I'm interested in this 4. This 4 is the Rasmussen invariant of the granny knot. And now we're done because this Rasmussen invariant is non-zero, it's 4. And the Rasmussen invariant is a group homomorphism from the concordance group to the integers with addition. And if the granny knot were sliced, the Rasmussen invariant would have to be 0 because it would have to be concordant to the unknot, and then the Rasmussen invariant would be 0. So that computation tells us that the granny knot does not bound a smooth disk. Yeah, so this Rasmussen invariant is a lower bound on the smooth slice genus, or you can think of it as a concordance homomorphism. Now, the Rasmussen invariant tells us that the slice genus, so the minimal genus of a surface whose boundary is the granny knot, is 2. And this is actually the precise answer. So this bound is sharp because here, if I draw this shading, that represents a genus 2 surface whose boundary is the granny knot. So having such an invariant like the Rasmussen invariant is extremely useful in low-dimensional topology. But now we again ask ourselves, where can we find such invariants? Where does it come from? And why are they sensitive to smooth surfaces in 4-dimensional space? Now, such invariants can be found using link homology theories. This is a research area that was pioneered by Mikhail Hovanov in the late 90s, when he showed that the Jones polynomial is the Euler characteristic of a link homology theory. That means it's kind of merely a shadow of a powerful type of knot invariant, and this link homology theory also explains why the coefficients in the Jones polynomial are integers, because they're Euler characteristics. Well, the state of the art is that we think of link homology theories as functors between certain categories. A few years ago, my collaborators Michael Erik, Dani Tubmauer, and I proved that a very large class of link homology theories, the Hovanov-Rosansky type A link homologies, can be described as functors. So that means, first of all, they send any knot or link in R3 to a certain Z2 graded vector space. And then secondly, any properly embedded smooth surface in R3 times interval is sent to homogeneous linear maps between the vector spaces associated to the links on both sides of the interval. There's a question.
Yeah, so this link homology theory is the same thing. This is also known as Chowanov homology, right? Or is it a
The
different
latter
theory?
is an example of the concept of a link homology theory.
Oh, okay, okay.
Yes,
And
there are several.
I already have the mic, so let me just ask a question regarding the spectral sequence you had before. How do you even associate a spectral sequence to a knot? I mean, you have a spectral homology theory, you have some homology theory, so I guess you can do it, but how?
So
And what does it compute at the infinity debate?
well, these are great questions, but I have to finish what I have on the slide before I can answer it. But I'll promise I'll come back to this.
Okay, thank you.
Yes. So
my question is much simpler, if I may, just a sanity check. When you say homogeneous linear maps, you mean preserving the Z2 grading, right?
That's not quite true, because because a link cobordism will lead to a map which changes one of the gradings by an amount that corresponds to the Euler characteristic of the link cobordism. Yeah. So and there, I mean, yes. So there's a predictable change in the grading.
So what do you mean by homogeneous then?
It doesn't mix gradings. Yeah.
Okay. Thanks.
Yeah. Otherwise, I would say grading preserving. Yeah. Okay. So let's do again. So what does it mean to be a functor? Link goes to vector space. Surface between links goes to linear map. And now you can compose the link cobordisms and you can compose the linear maps. And functoriality means that the assignment respects these compositions. And now I can say something about the spectral sequence. So the spectral sequence corresponds to a natural transformation between link homologies, considered as functors. So these spectral sequences arise if you compare two different link homology theories evaluated on the same knot. Sometimes you see that one appears as the E2 page of a spectral sequence, which converges to the other link homology theory. Yeah. This is exactly how the spectral sequence comes about. All right. So there are lots of, so it's maybe instructive to see how such link homology theories are typically built. Again, it uses generators and relations, and I won't have time to go into the details. I'll only outline the steps that are necessary, and then you can find kind of lots of resources, online papers or video talks and so on, which explain the details here. So the first step in any case is that you assign a chain complex to any link diagram. So there's going to be an algorithm which is very similar to the algorithm that I computed here on the screen, but this time it won't compute a polynomial, it will compute a chain complex. Next step, to every Rademeister move, you have to assign a chain map, okay? And not only to Rademeister moves, also to other changes of the link diagrams through Morse moves, where a little circle can be created or gotten rid of, or a little saddle happens. And to all of these things, you associate chain maps. And then it turns out that any surface that connects to knots or links can be presented as a sequence of these basic moves, Rademeister moves and Morse moves. And finally, you have to check some relations, but this time the relations are not Rademeister moves, this time they're one dimension up, and they're called the Carter-Cyto-Movie moves. They relate different presentations of isotopic link cobordisms. So this is just to show you some pictures of what this looks like and what steps are involved. So now there's an intriguing question, namely, why do link homology functors exist at all? And why do they work so well for extracting information about smooth surfaces in 4 dimensions? And to be honest, I don't know. I don't think I have a good answer. But I think if there's a good answer, it will be related to a much larger picture in which knot and link invariants are only one small piece. And maybe a modern perspective would be to propose that the Jones polynomial and Chowanov homology work because they're based, well, or even constructed from certain 3- or 4-dimensional categorical structures, which enjoy the same symmetries as little patches of 3- and 4-dimensional space, or space-time. And such structures seem to appear in nature, and they appear in different parts of mathematics, which tries to model natures. So they can, once one starts looking, these structures can be found in representation theory, in algebraic geometry, symplectic geometry, algebraic combinatorics, and in certain parts of string theory. So this perspective that I write down here is not a mathematical statement yet. Making this rigorous could be kind of a decade-long research project involving many people, but I think it would have exciting consequences. So, for example, the cobordism hypothesis of Byers and Dolan, for which a proof outline was given by Lurie, predicts that such algebraic structures, such higher categorical structures, should give rise to invariants of manifolds, for example, in dimension 4, which are computable by cutting and gluing manifolds. And I want to show how this could look in practice. So a few years ago, my collaborators Scott Morrison, Kevin Walker, and I built the first invariant of four-dimensional manifolds based on Hovanov homology. This is now known under the nickname of lasagna skein module. Lasagna because there are surfaces and four manifolds floating around, so two-dimensional pasta. Our invariant takes as input a smooth-oriented four manifold. And if the manifold has boundary, one also has to specify a link in the boundary, which may be empty. The output is a bi-graded vector space, and the construction uses generators and relations. The generators are certain diagrams of decorated oriented surfaces in the four manifold with boundary given by the specified link. This is the lasagna. And the relations use Hovanov homology. Moreover, the Hovanov homology of a knot in the three-sphere can be recovered as the invariant of the four-ball, where the knot specifies the boundary condition. So my plan for the rest of the talk, a little bit of time left, is to give you an update about what we found out about this invariant so far. So maybe the first goal was to compute these skein lasagna modules for four manifolds using cutting and gluing rules, and to assemble the invariant of a complicated four manifold from the invariants of simpler four manifolds. And the first question that you might have in the strategy is what sort of data structure we're using. What sort of data structure we're using to present four manifolds. And to warm up to that question, let's look at a related problem, data structures for two manifolds, like a landscape, like this one. So here's a map of a hilly landscape in Australian New South Wales, and it's a map used for long-distance orienteering race. There are many mathematical problems that one encounters if one does such an orienteering race. For example, a traveling salesman problem where one has to somehow decide which of these control points to visit first, in which order, and how to maximize the number of points that one gets in this way during a given amount of time. So the night race took 5 hours, say. And the winning team is whoever collects the largest number of points along the way without coming back late. Let's focus on the landscape. The most promising features here are the contour lines. The lines of points of equal elevation, which are spaced at 10-meter intervals here. So if you run along a contour line, it's completely flat. If you run perpendicular to the contour lines, then you follow the path of maximal steepness, either up or down. If we focus on this part of the map, we see some interesting features. So there are two saddle points here. Let's see. So there's one here, and there's one here. And there's one peak, a local maximum for the elevation. You can distinguish local maxima and minima because for maxima, the streams flow out. And if you look elsewhere on the map, you can also see local minima in elevation. For example, there's this little pond here. So these three feature types of elevations make up any large-scale map of a landscape. Okay, so let's see. Yeah. So okay, and in differential topology, this is explained by Morse theory. Morse theory implies that you can choose a height on any surface and a height function on any surface and cut it into basic pieces. Valleys, so neighborhoods of local minima in elevation, saddles and peaks. And any surface can be built by starting with the valleys, then gluing on the saddles, and then finally gluing on the peaks, proceeding from low elevation to high elevation. So in some sense, when attaching these puzzle pieces, the blue part of the boundary has to be attached to what you already have in this order. And here, of course, the shape of the puzzle pieces are unrealistic, but we're doing topology, so we can change to that, for example. So it's an important insight in Morse theory that similar building blocks also exist for manifold of higher dimension, for example, 3 and 4. And in the two-dimensional case, we had 3 building blocks, and you can imagine that, well, in dimension 4, you will have 5 building blocks, so always one more than the dimension. These are called handles. So an n-dimensional k-handle is a manifold with corners presented as the product of a k-dimensional ball and an n minus k-dimensional ball. For example, a two-dimensional one-handle is drawn here on the right. It's just a product of two intervals, so it's a rectangle. So it's drawn in a bent way here. We're doing topology after all. Writing the handle as a product is useful because the boundary decomposes into two parts, blue and gray. The blue part, topologically here, is a k-1 sphere times an n- k-dimensional ball, and it's called the attaching region. Along this, we're supposed to glue the handle to the boundary of another n-manifold. The core, drawn in green, is the k-ball by taking the first factor times the distinguished point in the second factor. So handles play for manifolds the same role that cells do in cell complexes. Along this analogy, a handle is a thickening of the cell that is its core. A core and the attaching region intersect in the so-called attaching sphere, and knowing where the attaching sphere, together with some framing data, is glued is enough to understand how the entire handle is attached. For example, the zero sphere is just a pair of points, and if you know where these two points in dark blue are attached to the surface together with some framing data, you know exactly how this rectangle is attached. The second example that will be of interest here is that in 4 dimensions, two handles are attached along their attaching spheres, which are, in this case, knots. Knots in the boundary of a 4-manifold. Okay, so this is the main connection between 4 manifolds and knot theory. Two handles attached along framed knots. Okay, so now we have two related ways of constructing manifolds. One is the bulk perspective and one is the boundary perspective. So the bulk perspective says we can build smooth n manifolds from n-dimensional k handles as a sort of thickened cell complex. The boundary perspective lets us build, well, at least some smooth n-1 dimensional manifolds as boundaries of n manifolds. So we run the bulk perspective 1 dimension up, and then we just look at the boundary and forget that there was a bulk, and we only remember the boundary. And an interesting example is this case of 4-dimensional two handles again. So if we attach a 4-dimensional two handle and B2 times B2 to the boundary of a 4-manifold, we can ask, how does the boundary change? The boundary of the 4-manifold. So if we only wait for a little ant that lives on the boundary of that 4-manifold, what we will see under a handle attachment is that a solid torus, the attaching region, is drilled out, and then another solid torus, namely the belt region, the complementary boundary of the 4-handle, is again glued in. And this is what we call Dehn surgery after Max Dehn. So out of a 3-manifold, you take out a solid torus and then you re-glue a solid torus in the same place in a different way. Now, this gives data structures for 3 and 4 manifolds. So there's a famous theorem by Licorice and Wallace that shows that any closed orientable connected 3-manifold can be written as the surgery on a link in S3. So on the other, alternatively, in the bulk perspective, that would say you can find any such 3-manifold on the boundary of a 4-manifold that is made out of a single 0 handle and then 2 handles. Kirby classified the ambiguity in this presentation, shows that 2 links describe in this way the same 3-manifold if and only if they're related by a finite sequence of moves called the Kirby moves. First move adds or removes a plus or minus 1 framed unknot, and the second one is called the handle slide. And we can use this kind of generators and relations perspective again to find invariants. Namely, if we find a link invariant that is constant on the Kirby moves, we found a 3-manifold invariant according to these 2 theorems, right? So you see, we're always using this kind of generators and relations idea. Now, let's try to see where such a 3-manifold invariant could come from if the only link invariant that we know is the Jones polynomial, okay? So first question, is the Jones polynomial already a 3-manifold invariant? Is it invariant on the Kirby moves? Answer, no, it's not. let's ask a different question. Is something related to the Jones polynomial invariant under Kirby moves? Here the answer is yes. And how does it go? Well, instead of computing the Jones polynomial of the knot, let's compute the Jones polynomials of a family of links that are related to a knot. So for example, if we start with the trefoil, we can also compute the Jones polynomials of the double trefoil, the triple trefoil, and so on and so on. Okay, to do this precisely, I actually need a framing on the knot to tell me what sort of notion of parallelism I take. Okay, but that's something we can do. And in this way, we've upgraded our Jones polynomial, which is one polynomial, to an infinite family of polynomials. Okay. Now, what we can try to find now in our collection of link invariants, which has now substantially increased, we can ask, now, is there a linear combination of such Jones polynomials that will be invariant on the handle slides? So will be invariant under the second Kirby move. And the answer is yes. So if you make an ansatz, I want some linear combination of Jones polynomials that is invariant on the handle slides, you will find this is a solution. There's some particular linear combination that does the job. The problem is it's infinite. So that means if you plug in complex numbers, the sums will typically not converge. So this is kind of a formal sum that has the right properties, but it doesn't converge. And then there's a trick. So one can specialize this parameter a to a particular complex number, to a root of unity. And then it turns out one can make the sum finite. And then one runs into a second problem. So then one has a finite sum and it's constant under the second Kirby move, but it doesn't satisfy the first Kirby move. However, then there's another trick one can do because the failure is somehow an invertible scalar and you can just multiply by the inverse and fix that. And if you do both of these kind of fixing steps, you obtain the Witten-Reshetikhin-Turaev invariants, which were developed in the 90s, based on the Jones polynomial. Now, this was a three-dimensional story. Let's see if we can do something with link homology, and I'm getting very close to the end, so sorry for, yeah. So let's ask, does something similar work for Khovanov homology? So is something built out of Khovanov homology invariant on the Kirby moves? Well, the answer is yes and no. So this is based on joint work with Matt Hogenkamp and Dave Rose. So here's a selfie that we took at a workshop in Oregon after we finished the paper. And so what do? We take Khovanov homologies of all cables of our favorite knot, and we also need to know cobordism maps between them, right? So in link homology, we have two levels of structure. We have these vector spaces and we have the linear maps. And then instead of writing down a sum, we find a filtered colimit of these Khovanov homologies. And then it turns out this is invariant on the handle slides. And then there are two more steps and we just throw them away. And in particular, this will not be invariant under the Kirby 1 move, and we're actually happy about this, as I'll explain. So our work built on a really cool paper of Ciprian Manolescu at Stanford and his former student Ikshu Nathaleth, and subsequent work with Walker and Manolescu from 2020 to 2022. And what the main outcome of this sequence of works is that these skein lasagna modules, these four manifold invariants, can be computed along handle decompositions. And if you see how these skein lasagna modules change under two handle attachment, then this precisely corresponds to this computation of the filtered colimit on the previous slide. So in this sense, this Kirby colored Khovanov homology, this filtered colimit that I had on the previous slide, computes these skein lasagna modules of two handle bodies. So yes, this gives an invariant, but surprise, it's an invariant of four manifolds, not of three manifolds. Then I said, we're gonna throw away the last two steps. So there was this convergence issue. So for the Jones polynomial, we were computing these infinite sums and that caused problems. Well, it turns out that if you work with vector spaces, infinite sums are not a problem. Infinite dimensional vector spaces are totally fine. They might not have finite dimensions though. So there's kind of open questions related to when these vector spaces are locally finite dimensional, so finite dimensional in each degree. Finally, about this rescaling issue, so we don't have invariants under the first Kirby move, and this is related to these invariants being honest 4-manifold invariants and not 3-manifold invariants. They really depend on the 4-manifold, not just on the boundary. And this is good because this gives hope that these could detect exotic smooth structures. So this is really my last slide with content. So I want to give a bit of an outlook of things that are currently happening in this research area. The first one is a project with Leon Leo, Earl Maisel G, David Reuter, and Katharina Stroppel, where we reached the first milestone earlier this year. And we have a joint paper in January. The eventual goal of this project is to upgrade these 4-manifold invariants from the homological level to the chain complex level using tools from higher category theory, infinity categories, infinity operats, and the like. And this would give the very first example of a fully extended 4-dimensional TQFT in a derived and categorified setting. Katharina Stroppel talked about this project and our first steps towards this goal in her plenary ICM talk 2 years ago. If you want to hear more about this, you can find this online. Second point, where I see a lot of potential, is the connection to physics. So about 10 years ago, Witten proposed a physically motivated explanation of Hovanov homology, which has formal similarities to lasagna skein modules. So for example, knots have to be considered as living on the boundary of a 4-manifold in this setting. Computing Witten's invariant is analytically very hard, so we don't have comparisons yet. More recently, Mina Ganagic has proposed relations between knot homology and homological mirror symmetry, also motivated from physics. And if you're interested in that sort of direction, there's also an ICM talk by her on this topic. And so finally, the most exciting development in the last few years, for me at least, is that a growing group of young topologists are using link homology theories and related categorical methods to prove really exciting new results in low-dimensional topology. For example, as of February this year, we know that these skein lasagna modules detect exotic smooth structures, and this gives, as was mentioned, the first algebraic proof of the existence of exotic compact-oriented 4-manifolds in the work of Wren and Willis. So there's a lot more to do in this research area, and I would be very happy to see some of you people do research here. So this is it. Thanks a lot. Maybe one more thing. So I'll use this opportunity to advertise the research center again. So we have master programs in mathematics and mathematical physics, including qualifying scholarships, and then PhD and postdoc position, and lots of conferences and workshops. If you're interested, feel free to contact me if you're interested in any of this. Thanks a lot.
Thank you very much. Have you answered all the questions? Because there was a question and you said you would answer at the end.
So I'm sure I have not answered all the questions. I think there was one question about, I think there were 2 questions that I was hoping to answer over lunch. But, yeah.
About lasagna, of course.
About lasagna, yeah. Lasagna for lunch?
Yeah, exactly.
Yes, that sounds good.
Okay, so are there any questions right now, maybe?
I do, but maybe there are some other people.
There are two people
in the room. Yeah.
Okay, so I have 2 questions actually. So the first one is, you used the phrase data structure a few times. So is this actually something you use to like automate some computations? Can you or maybe do you see the possibility of like having a computer do the computational work with these kinds of invariants?
That's a great question. So the answer is yes, I would like to. So somehow I feel more like an algebraic person than an analytic person. So you could have invariants that are described as bases of solutions to some PDEs related to your manifold, for example. That would be kind of very often such invariants have wonderful properties, but space of solution of PDEs makes it really hard to compute in general, right? So I'm looking for invariants that have at least some algebraic recipe, or what I hope that there's some algebraic recipe to compute this. And for this, I want to have some sort of discrete presentation of my manifold. I want to be able to describe my manifolds combinatorially, and from that get a recipe to compute the invariant. Whether this will be of a suitable format for a computer to tackle is a different question, because, for example, in the thing that I presented, we need kind of Havana homology for an infinite family of knots. That's not something I can give to a computer, right? So, or at least not without having some additional results. So, for example, a result that I would like is something that tells me that if I look in a specific grading of my invariant, right? My invariant is highly structured, it has these gradings. I want to say, if I look in a particular grading, then I only need to do a finite computation to compute the answer there. That would be nice. If one can prove such statements, but these will be mathematical statements, then it would be somehow a good idea to write a computer program that computes in that degree. And then I can somehow efficiently approximate my invariant to some, up to some error, basically. So yes, so I would love to get invariants that are computable in this fashion, or at least can be approximated efficiently.
Okay, there was...
Yeah, so if I can ask one more question. So in the talk, we've seen a lot of structures given by like diagrams with some sort of moves, or generally structures with some sort of moves. Is there a general strategy you can use to show that these moves are enough to describe all the rigidity? Because that seems like a very hard problem, even for something as classical as Morse diagrams, for example.
Yeah, that's right. That's always a problem. And it's one problem that you have somehow for each type of diagram or something that you use. And this is somehow where, I don't know, in the last 10, 15, maybe 20 years, there's been a lot of progress, because kind of these diagrams and relations between them, and then often you have higher relations between the relations and so on. This is exactly what somehow higher category theory is designed to do, to describe such hierarchies of relations and so on. And this is, yeah, after all, somehow what is happening here, just to drop a few words, these four-manifold invariants are associated to some local datum, so something that you assign close to a point, or say to a four-ball, which takes the shape of a braided monoidal 2 category, or a or kind of an infinity categorical version of that, an E2 monoidal infinity 2 category, which is somehow the universal thing that encodes tangles in 3D and surfaces in 4D, as well as all their isotopies and so on. So there are kind of there are strategies for handling this, but as you say, it's typically a hard problem, and it will be a hard problem for every type of diagram that you consider. Yeah.
Okay, thank you.
Okay, I think that Bartek Szachniewicz wants to ask a question.
Okay, so my question is that you talked some things about this higher category theory, and I was wondering if there is maybe some, if you know, if there is like maybe some model theory work done on it, because like so far when you have category theory, model theory can often express some ideas in category theory, but in other language. So I was wondering if you can like, if there was any work done on expressing the ideas from higher category theory, but done in model theory. If you know something like this exists, maybe.
So there are definitely connections, but this is maybe also a question for lunch.
Okay, so see you at lunch.
Okay, so sit down with him at lunch. Yeah,
Yes,
please.
So, thank you for the beautiful talk. I have two pretty general questions, I'd say. I tried in the past to read something about knot theory, but I end up kind of losing the point of what I'm doing, really. So seeing some applications to biology and chemistry kind of motivated me, but I want to ask if there are some problems, even in actually better if in mathematics, but also like in applied sciences, that could be resolved using knot theory, and if there's some work on that. And linked to this, I wanted to ask you what drew you to study knot theory first, and how is your interest evolved in the field during time?
Yeah, thanks for the two very different questions. So maybe I'll start with the second one because the first one I just know less about. They're somehow they're experts who really do that, and I can recommend you a few things to read maybe. But about the second question, so actually I wouldn't consider myself as a knot theorist. Somehow it just happens that the thing that I started studying in my PhD were these link homology theories, and I was really interested in the sort of algebraic structure that is captured by them. And basically, when I started my PhD, there were lots and lots of conjectures about these link homology theories and how the different ones are related, which came from physics. And so what I started doing is somehow to prove some of these conjectures or somehow to refine them and then discovering more structures. So this is basically how I got into this. So it happens that they are invariants of knots, but nowadays we also know that they give invariants of manifolds, and somehow this is branching out, and it's connecting to lots of different areas in mathematics, because these, after all, these higher structure, so these link homology, so there's knot theory, and then there's these particular invariants for knots, and then it turns out to make these invariants, you have to have some higher categorical structures in the background, and they seem very universal. They seem to show up in many places, and so this is somehow what fascinates me most in this area, and this is also why one can talk with lots of people and working in very different areas, and because many people are seeing the same structures. That's what I find really interesting.
Thank you.
Okay, Piotr, would you like to ask a question?
Yes, please. So could you please go back to the slide where it's showing that the reef knot is a slice?
Okay, let's see. This one, right?
Yeah.
Oh, it's
okay.
Sorry.
Yeah. So let me ask it as an open question. I might be completely wrong, and this is very speculative, but I cannot resist the temptation of posing this question. I somehow have a feeling that this slice trick you do for the reef knot would survive a non-commutative deformation, because we have Hong-Szymański quantum 4-ball. It has as the boundary the quantum 3-sphere Waxman-Soibelman, which is given by precisely the same sister algebra as Voronovich's SUQ2, which was explained by Sultan in the first lecture. And we have exactly classical circle inside this quantum 3-sphere. And I have a feeling that we could have that this circle in S3, this reef knot circle, could be the boundary of a quantum disk, because there are lots of ideas of compact operators in the Hong-Szymański quantum ball construction. So that's a very speculative open question, but somehow I cannot resist the temptation of mentioning it. Okay. Now, next thing is you mentioned Witten-Reshetikhin-Turaev invariance. Is it? I'm aware of a Reshetikhin-Turaev paper which was based on quantum groups. How these two things are related?
Yeah, thanks for the food for thought and the question. So I think it's for the first thing, it would be really nice to meet over lunch, but you're not here, right?
He's here.
Oh, you're here.
I'm here.
He will be at
Oh,
lunch,
fantastic.
yes.
Well, then let's take over lunch. Okay. Now, second. So Reshetikhin-Turaev. So, what is the connection to the quantum group? The quantum group. So what one does is one studies the representations of the quantum group.
Yeah.
And then this turns out to be a category. Well, actually, it turns out to be a monoidal category. And then this also has a braiding. And so that turns out to be some three-dimensional categorical structure. And associated to this is a three-manifold invariant. And that's the Witten-Reshetikhin-Turaev invariant. Story is actually a little bit more complicated, because it turns out that there's a a 4-manifold invariant also, and then you look at the boundary, and then you see which relationship you can derive. But the upshot is studying representations of quantum groups gets you to 3-manifold invariants.
Excellent. So let me end with a very quick remark. It's not a question, but I find it fascinating. You see, there is a paper of Kaufman and Radford from 1995, I believe, which you as a not theorist might know, where they defined a certain algebraic structure in Hopf algebras. I mean, Kaufman is a not theorist and Radford is a Hopf algebraist. And they defined some additional structure in Hopf algebras, like sort of, it was like sort of a square root of the famous Radford theorem that S4 about the fourth power of the antipode in a Hopf algebra. And the structure was used for knot theory. I don't know how, but it was used exactly to apply and answer some questions in knot theory. And it is a modular plane involution. And remarkably, 5 years later, completely independently, studying foliations, Kohn and Moscovici discovered precisely the same fine-tuned structures of algebras. So for me, it's kind of a puzzle how two very specific, very subtle algebraic structures in Hopf algebras can be discovered on one hand side because of knots, and on the other side because of foliations. It's for me, it's remarkable. It's just a comment how I come to like knot theory.
Yeah, that sounds very interesting. I mean, if I think I only know like part on the part of one half of the story that you just recalled, and if I remember correctly, this is somehow related to these particular Hopf algebras giving somehow 3-dimensional algebraic structures with similar symmetries as a 3-dimensional ball. And on that, you have SO3 acting, and that has a fundamental group sigma 2. And I think the square of the antipode is just that generator, and if you square it, you get the trivial thing. So it turns out again to be related to symmetries of 3-dimensional space in some sense, if I remember this correctly, which is not guaranteed. Yeah, but thanks for the remark.
Yeah, thank you so much.
Yeah.
Okay, are there any questions from people on Zoom?
Sorry, I'm on site, but still I have one question if I could. So you mentioned something like showing that some knot, maybe not some, maybe for a more bigger class of knots, that these are knot slices, is somehow related to this smooth Poincaré conjecture. So could you repeat that?
Yeah, so maybe in the interest of time, I'll refer you to a paper titled Man and Machine Thinking About the Smooth 4-Dimensional Poincaré Conjecture, which outlines strategies for potentially disproving the conjecture by using things like that. And there's also more recent
Could you repeat the title?
Yes, Man and Machine Thinking About the Smooth 4-Dimensional Poincaré Conjecture. It's about like 10 plus years ago. And then there's more recent work in a similar direction by Manolescu and Piquirillo from 2 years ago, maybe, or 3 years ago. So they had a few more candidates that when you show non-sliceness, this would have implications.
Okay, thank you.
I think we may continue discussions at lunch and also after lunch. I guess you are available until 5 o'clock.
Yes.
So please just organize yourselves. And let me just ask one final question for the people on Zoom. Are there any questions or comments from people on Zoom? Okay. If not, let's thank the speaker again. Thank you for the beautiful. Okay, and the session is over, and yeah, we may proceed to the lunch.